Hello, everyone. In this video, we're going to prove three theorems about identity. These three properties of identity were introduced weeks ago when we introduced the identity sign to our language PL. They're there across the top of the screen. The first one is the reflexivity property. For all x, x is identical with x. It says everything's self-identical. The second property is symmetry. For all x and y, if x is identical with y, then y is identical with x. The third property is transitivity. For all x, y, and z, if x is equal to y and y is equal to z, then x is equal to z. So we're going to prove each one of these statements as a theorem. That means we're going to get the statement along the main scope line of our derivation without any primary assumptions. The proof of reflexivity is very, very easy. So I've got it set up there on the left side. We're to derive for all x, x equals x. So I've gone ahead and introduced it along the scope line where it needs to be, and then all we need to do is show how we're going to get it. And it's going to be pretty easy because we have this rule, identity introduction, that allows us to insert a statement exactly like that theorem on any line of any proof without citing any line numbers, and it doesn't require a subderivation. So that's our first proof of the first property of identity, reflexivity. Now let's go ahead and turn to the second property, symmetry. Here's the derivation set up for the proof of symmetry for all x and y. If x equals y, then y equals x. And we're going to do a little bit of goal assessment here. This is obviously a universal generalization, so universal introduction might be a good strategy for proving it. So what we'll need for input is an instance of the generalization we're after. So for all y, something like this. If a equals y, then y equals a. That's itself a universal generalization. We may get it by universal introduction on one of its instances. For instance, this. If a equals b, then b equals a. That statement is a conditional, so we're going to use conditional introduction to get it. So here's the subderivation. We're going to assume a equals b on line 1, and then we're going to derive b equals a by the end of the subderivation. That's an assumption for conditional introduction. We're assuming the antecedent, and we're going to derive the consequent. The proof is, the subderivation is not very long. We're going to make a move that we made in the last video. A equals A, treating line 1 both as the context for substitution and the identity justifying substitution in an application of identity elimination. And then on line 3, we're going to get B equals A from 1 and 2, identity elimination. That gives us the consequent of the conditional, so we can cite lines 1 through 3, conditional introduction. And then on line 4, we take line 4 as input for the first application of universal introduction, and line 5 as input for the next application of universal introduction. And that ought to be line 6. So there is the proof of the second property of identity, symmetry, that it is a theorem. We prove it by first proving the conditional and then doing universal introduction on that 2 times. Okay, so next let's look at that proof for transitivity. Okay, here we have the proof set up for the transitivity theorem, and it's going to follow some of the basic strategies of the previous proof. We have, again, a universal generalization across the bottom. We're going to derive that by universal introduction on an instance. The instance will start with the y quantifier for all y for all z. If a equals y and y equals z, then a equals z, which is itself a universal generalization. We'll derive by universal introduction on one of its instances. For all z, if a equals b and B equals Z, then A equals Z, which is itself a universal generalization we'll derive by universal introduction on one of its instances. If A equals B and B equals C, then A equals C, which is a conditional, and we'll prove it by conditional introduction. But before we do that, I just want to point out these names, A, B, and C, in these different positions have to be different names. We cannot have all A's in here across this conditional and then get this line by application of universal introduction. We need to have different names in those different positions throughout the basic conditional. Okay, so we're going to prove this by conditional introduction, which means we'll start a subderivation on line 1. And then we will need on line 1, we will need the antecedent of the conditional, A equals B, and B equals C as our auxiliary assumption for conditional introduction. And then we're going to need A equals C as the last line of that proof. The obvious move here is to break apart the conjunction on line 1, A equals B, and B equals C. Both come from line 1 conjunction elimination. 1 ampersand E. Well, if A equals B and B equals C, then line 4, A equals C, taking 2 and 3 as input for conditional elimination. And this is one of those instances where, because of the order of the names here, it really doesn't matter whether 2 is the context for substitution and 3 is the identity justifying substitution, or vice versa. We could think of line 3 as the context, in which case B is taken out of line 3 and A is put in for it. So we'd move from B equals C to A equals C because we substituted an A for a B. Line 5 then would be 1 through 4 conditional introduction. Line 6 would be 5 universal introduction. 7 would be 6 universal introduction. And 8 would be 7 universal introduction. I will point out what I might have stopped and pointed out in the last proof. We did universal introduction here, here, and here. We did universal introduction on line 6 here on the name C. And you notice we did take both occurrences of the name C out and put a variable in, Z, okay? So we respected the proviso on universal introduction that the name we're replacing with a variable doesn't end up staying in the result of the rule application. The other proviso on universal introduction, remember that one's the kind of touchy one. The other proviso says that the name, in this case C, cannot appear in any live assumptions. Well, it's in an assumption, isn't it? It's up there on line 1, and line 1 is an assumption, but it's not a live assumption on line 6, which is where we're applying universal introduction. The name C, while it appears in an assumption, that assumption's innermost scope line has stopped growing on line 4, which means C is fair game. We can apply universal introduction to that name. The same would go for B and A on the next 2 lines. Okay, so there are 3 little theorems proving some of the interesting properties of identity: reflexivity, symmetry, and transitivity.